Well, I think I'm going to pick up again and wrap up here in the next 30 minutes or so. Dropped off right before talking about really important issue of conductivity in gaseous media, and this is a vast subject, lots of literature on it. We're only going to cover a couple of slides here, but I think a point to understand, in a conventional electric generator, you have a long copper wire that moves at a relatively slow speed through not a gigantic magnetic field. The conductivity of the gases in MHD system is relatively low, even when you seed this, as on the next slide here. MHD power is only practical because you have this high velocity, strong field, and a large volume conductor, and adequate conductivity. So I'm going to define what I mean by that here in just a second. But let's go back and actually see what I mean, quantitatively. We actually derive this real quickly, the power output density, and we have that load factor in there, K, and then remember I emphasize the point, proportional to the square of the velocity of the gas, the square of the magnetic field, but then the conductivity right here, all right? So what's the conductivity? Well, I mentioned like in a copper wire, order of magnitude 6 times 10 to the 7 reciprocal ohms. In seeded MHD, it might be 10. All right. Well, 10's a big difference from here, but again, you have squares of velocity, where if you imagine this high temperature flow, you're talking about 1,000 meters per second, right? Very high. Square that. Compare that to like 10 meters per second, like, rotating an armature or something like that. So you see, I can make up the difference there. And also, this is power output density. Unlike a copper wire, which is small, we're talking about a large volume of gas, right? So even though I might have a lower specific current density, I've got a larger volume than if I had a discrete copper wire, all right? So is it clear like why you can make this into a power generator even though you have low conductivity compared to conventional wires, all right? So that's how this works. Now, you do have to have some conductivity, and a conventional gas, a combustion product, is not conductive enough, all right? I just mentioned the current flow depends on the conductivity times the electric field. We just showed this expression for power density right here. You can get a sense of how much you need here. Load this thing up at a load factor of 0.5, and that would give you the maximum power that you get out of here. Just look at that expression right there. So K is 0.5 for the maximum power. Plug that back in here, maximum power, conductivity, square velocity, square of the B field, divided by 4, the product of those two. So for a reasonable design, if I want a power density of 10 megawatts per cubic meter, so in other words, if my channel volume was a cubic meter, again, which is reasonable, all right, I plug in realistic numbers for the product of UB and then square it, you can solve that and show you've got to have a conductivity of about 10 reciprocal ohms, or the units Siemens per meter right there. All right, so that's the kind of conductivity that you actually need to achieve to get working MHD at some reasonable scale. So here's an example of some data from a long time ago, way back in '74, but just a published piece of data on conductivity versus temperature for combustion products that are seeded with 1% seed of potassium right there. This is the ionization potential of different species that might exist in the flow. You can see very high ionization potentials reported in electron volts for all the gases that we're used to working with. And so the message there is that you're not going to get much conductivity out of those. There's just not enough energy to poke an electron off of those gases. But if you put in even a small amount of some of these seed materials, they have an ionization potential much lower. And so depending on the temperature, you can get to values of conductivity that are reasonable for MHD power generation. And so I said right here, we're trying to get to about 10. Well, there's 10 on that scale right there. And you can see if you drop the temperature much below about 2,500 Kelvin, you start to lose enough conductivity to have useful power generation. That's why this idea of MHD only would make sense if you were doing oxy-fuel combustion, because you have to have very high temperatures, unless you can find some way to make the gas conductive that doesn't rely on thermal equilibrium of ionizing electrons off of the seed material. Let's keep going here. Well, it turns out we looked through some of the literature for conductivity from the earlier MHD program, and actually there was a tremendous amount of uncertainty in what conductivity would exist in the gases that we were interested in. Enough that our calculation of the power density was uncertain within a factor of 4 or more. So you say, I'm going to try to actually say, how well could I generate power with one of these devices? And I don't even know precisely the conductivity that I need to do a simple model of what's going on in the device. So we said, well, a very simple experiment we can get started with is just studying the conductivity in gases at the conditions that we're interested in. So we put together an oxy-fuel burner, pure oxy-fuel, and started operating it. You know, began operating this last February. You can see the flame here. It doesn't always have this interesting character. It is a Henkin burner, so there's fuel and oxygen in these small channels right next to each other. So you get these little small discrete flame regions right here that then quickly mix out, and you basically have a plug flow region where you've got the products of combustion moving up into the lab. And we have not put the seed in here yet, but we're planning to do that to actually make the conductivity measurements. A lot has changed since people tried to make these type of measurements, 20, 30 years ago. Today we do things like planar laser-induced fluorescence pretty routinely in labs to measure things like, well, what's the profile of, for example, OH in the flame, and can we back out other species from those types of measurements. Turns out you can also do K-PLIF, and we're planning to do that when we put the seeding into the flow, and you can also, of course, do spectroscopy. So this is quite a bit different than what people were able to do 20, 30 years ago. That's my point on this slide, is we're starting to take quantitative measurements of what's going on in these flames, and then, of course, measurements of their conductivity. Unfortunately, right now, we don't have any better way to measure conductivity than with Langmuir probe. You think, now, how am I going to do that at 3,000 Kelvin? But, the probe goes in and we pull it out in a matter of milliseconds, and you can actually make a conductivity measurement. It's not the best. I wish there were a better way, but we've looked at the literature and some of the more advanced techniques. We're just not willing to sign up for it yet. But we need that data to actually make measurements or to make predictions of the performance of one of these devices at oxy-fuel conditions. So we are looking at the seed addition, and there are mechanisms available that calculate all the reactions that might occur with the seed that we inject into the material. Probably I'm less comfortable with the fact that we've got quite a bit of uncertainty in data for how the electrons come off that seed, so we don't have good kinetic models there yet. We're just starting this. We may have missed some of that literature. If there's anyone working in this in the audience, please direct us if you find better literature on some of the rate coefficients here. But we're starting to put the mechanisms together to do predictions of what's going on in these flames. And I'll just mention, I went the wrong way there. You can do the kinds of things you're all familiar with here, running a 1D equilibrium code and then a 1D kinetic code, 1D kinetic code to predict, what are the species that exist post-flame in these particular situations. And we've compared these chemical equilibrium codes, the CEA equilibrium, to the Cantera case where you've got a burner stabilized heat losses, and you pretty much get to what you'd expect for equilibrium in a short distance off that burner. That's millimeters, and you can see after we go through the burner phase, we get to equilibrium very quickly. So here's an interesting question. Back up. Remember what I just said. We get to equilibrium right after the burner phase, at least based on these codes, in just a few millimeters. So let me show the flame again. So we said, okay, we're at equilibrium. So I asked, our combustion group, well then, if we're at equilibrium, why is it still glowing blue? And I thought that was just such a simple question. I was saying which species is responsible, because it was a really distinct blue color at that condition. And I found out we didn't actually know. So we're going back in and doing spectroscopic measurements. We were all debating which species it was. Why? Because the temperature conditions here are so much higher than what we're used to working with. We don't actually know the line transition. But it was a clue to me. It's not quite at equilibrium, right? Why else would it still be emitting? So we've got a little bit of homework to do on which species are involved there, but there are still electronic transitions occurring, or it wouldn't be giving off that faint blue. So I don't know if there's something there that we need to pursue or not. But by the way, this is in the absence of any electric or magnetic field right now. So we start to put those on, then I'm going to be accelerating those electrons through there, and can I get any extra ionization from the motion of those species? I just don't know. We don't have the mechanisms in place yet, so we are learning this. That's why this is what's the name of this session? Advanced combustion, or new developments. We're actually trying to understand what's going on in this particular flame at these conditions, because the conditions are unique to these high temperature oxy-fuel flames. Well, we're getting this set up right now, and I just thought I'd show you a picture of the Langmuir probe. It's sitting there. The probe tips are right at the end there. It's mounted on this device, and it translates in and out of the flame very rapidly in the order of a couple of milliseconds, and we're just starting to make those measurements. So I can't tell you, how well we're doing in terms of predicting what we expect from that flame, but we're getting our feet wet and understanding the conductivity even without the seed. The seed comes next, and of course we want to get our baseline measurements before adding the seed, because it'll cloud the burner, and we'll have the sodium, potassium in the flame. Okay. So I've talked about seeding the flow to produce the conductivity that we need for this system, and I just want to stop at this point and raise this question: do we have to add the seeding to make this flow conductive? The seed recovery was a major cost item and a barrier in the earlier MHD attempts. Now, things have changed a lot in the system that we're talking about, because today you want to think about, can I actually do oxy-fuel combustion and capture the whole exhaust stream? All right? So say I'm going to put a seed in there to make it conductive. Well, you're going to condense the whole exhaust stream, right? It's very different than the earlier program where you're emitting some stream into the air. So here, capturing the seed is a much different issue than it was 20 or 30 years ago. It's just not the same at all. So we did a little economic study on that. It doesn't look like a big barrier. And the other thing that's very different today is, at that point, the seed recovery was also being used as a way to catch all the sulfur. So you had a whole bunch of process steps to take care of the sulfur in that scheme that were distinct. Here, you're just going to condense it all down. It's all going to come out as one part of the process. So it's a very different process potentially today that you wouldn't think about doing in the earlier MHD program. So that was my point here. That whole seed recovery's got to change if you're going to do carbon capture. Now, one of the things that I'm really hopeful we'll find a positive answer to is, if you could generate a non-equilibrium plasma, it would be a game changer. Right? By non-equilibrium plasma, I mean make the flow conductive by creating conductive plasma, like in a fluorescent light or something like that, so it's conductive without requiring that high temperature. Why is that so significant? Why would it be a game changer? Well, if it didn't take a lot of energy to do that, and you could make it conductive at even lower temperatures, then you'd keep getting enthalpy out directly, all right, all the way down that temperature window, right? Temperature's coming down, but if you had a non-equilibrium that you could keep it conductive, then you could take energy out all the way down the temperature, and your bottoming cycle then could be matched right up to the exit of the thing. Well, I don't know if we can generate a non-equilibrium plasma like that. You obviously can't spend all your energy making a non-equilibrium plasma. That wouldn't make sense. And then even if you have low energy to make it, it can't just recombine, right? The electric force between an electron and ion is very large, right? So they're going to try to recombine very quickly, and so you have to have a low enough recombination rate. There have been people that have been thinking about this, and I just learned of one other from our friends at PPL here. For propulsion applications, this particular paper, they looked at nanosecond discharge pulses, which again, I don't think they had that technology back 30 years ago, and they were looking at it for that propulsion cycle, where you would try to inject through nanosecond pulsing, generate non-equilibrium plasma, inject it into the flow, make it conductive, and then pull power out in that way. And at least this paper said you're about 2 orders of magnitude off. Just can't get there, can't get enough conductivity. Okay, that's one, maybe that's one option we cross off the list. but it was just an analysis, right? It wasn't detailed looking at, one of the things that bothers me, I'll just say, one of the things that bothers me about the experiment we've set up, I wish we could find a simple way to change it. We're measuring the conductivity in that seeded plasma, but we don't have any magnetic or electric field on it. Right? Well, if that field were really there, then I'm continuing to sweep the electrons through that region. I'm putting kinetic energy in. Is there a way I can take advantage of that and change the conductivity? I don't know, right? But that's just the limitations of what we can currently measure. So we'll have to move forward and make some additional assessments of that. All right, we also have to, before leaving this subject, talk about how you get the electricity out of the device, the electrodes. I mentioned this earlier. It was a big part of the early program is how do you keep the electrode, here's an example of one that was taken from this legacy test program, how do you keep it from getting damaged if there's an arc? A lot of these were cooled. I think that's the electrical wire there, and then they were cooled water in and out at this point. But it's not just cooling that surface. If you did this, for example, with coal, then you've got to worry about chemical attack, right? Because you have all the coal ash at those very high temperatures, and you've got to worry about, this electrical attack from arcing, focusing energy down into the electrode surface itself. In spite of those complications, there were some tests in this legacy program, particularly the devices that were operated in Russia. I mean, they ran a long time. Those weren't coal applications there. But it suggests, yeah, you probably could make an electrode that would work in this environment. And more of interest perhaps today, there's new ways and new materials that we can consider that just weren't available back, when this was thought about for the first time. We're looking at this field-assisted sintering technology, and the way this works. This is now commercial technology to make some advanced materials. But the reason why we're looking at it is the sintered material. You put a powder in, you can apply pressure and then use pulsed DC voltage, which in simple terms creates enough thermal energy at the point of contact of those particles that it helps you sinter with very high densities. This is what I'm told, and we think that might enable us to create electrode with more durability from a conductive ceramic. So we're trying to understand whether that is possible or not. The other thing that's changed today, I mentioned arcing. Well, we have very fast electronics today, so if you start to see incipient arcing, you may be able to react with the electronics to actually change the load on a particular electrode and avoid damaging or avoid the start of an arc that could burn the surface. We don't know that yet, but it's, again, something we'd like to try to assess as we start to look at this technology. So, how would you actually do this in a real power plant? The sketch that I've got up there was a potential layout from the legacy MHD program, and you can see, there's a conventional boiler as the bottoming cycle. There's the radiant part, but here's the MHD tube. So from a view from the side, you can see the magnets located here with this MHD tube, where the exhaust then goes into the radiant part of the furnace, and then the convective pass back in here. So this stuff all looks like a conventional boiler, but you add this topping cycle, the MHD portion up in front. So what would change dramatically if you were interested in catching the carbon dioxide and you were going to use pure oxy-fuel to drive that? What's the first thing you'd say is going to disappear off that diagram? It's not a trick question. What's that? The chimney, the stack, right? You're saying if carbon capture is my goal, I'm not going to have any emissions. I'm just going to condense the water out, and you're going to compress the CO2 and store it somewhere, right? So that part changes right off the bat. There's a couple other changes here that, if you think for a minute, it'd be really interesting. If you were going to look at some future for the electric grid, all right, if you work in that area, you realize there's people that talk about high voltage DC transmission. Interesting. I mean, look at the size of the inverter, because MHD obviously generating DC power, right? Well, maybe you just go right to high voltage DC. All right, so I'm not sure that would work or not, but it's a very different thought, right? Because with MHD, you can go directly to DC power. I'm not sure the voltage levels match up directly, but it's an interesting difference that exists today that wasn't something to think about at the particular time. So there's a couple of major differences if you're going to do this in a scenario where you're trying to do carbon capture. Make sure I've got them all. Okay. So there's a whole slew of research issues here. I really did mean when we say new developments in combustion technology, this is something we're just starting to explore. Does it make sense? Is this a viable strategy? Well, you know, if you look through different literature citations, you get different efficiency benefits of the concepts I've described. So the enthalpy extraction from the combustor to the MHD exit, that's really the key. How much energy can I get out in that tube? It's got to be a big number. And I've talked about the conductivity versus the temperature in existing concepts. You can't get below like 2500 Kelvin and the conductivity is just gone. You're not going to get any power out. The steam cycle I would couple to, you know, what, 800 and 200, about 1100 Kelvin. So now I have this temperature gap where I'm getting nothing. That's really not the way to configure an efficient system. That's why, if you think about it, one of the keys to really jump that up is to get more conductivity down the axis of the device. So there might be some other, there's this citation, it's now 10 years old. There's some interesting options in there if you want to go take a look at it. But this idea of conductivity versus temperature also very important. You know, this bullet that I have here, research issues, very different from when people thought about developing MHD 2-3 decades ago, right? Because they would move quickly to trying to scale things up because there wasn't a way to assess performance. Well, the point today is ideal application for advanced computing, for cyber combustion, but then also here plasmas. Can I predict this so that the only thing I need to develop test-wise is components to give me data to make sure I understand the physics of what I'm doing? Even if we go to these validated simulations, where do you get the data? That's why we said, well, a simple thing we can do is get conductivity data from a lab experiment and then use CFD to look at, well, what's the performance, you know, in a predicted environment. So that's why right now we've only built small experiments. We don't want to go above that. And then there's some very far out ideas that, you know, we might think about going into the future. What about unsteady flow? Could I get MHD power out of unsteady flow? We just, you know, or this afternoon talked about rotating detonations. So unsteady flow or PDEs. If you look through the literature, you'll find there are people that have suggested this. There have been some analysis. It's an interesting thought. It changes what you actually do, you know, in an unsteady flow. And then these non-equilibrium plasmas, you know, could you sustain one behind a detonation? Because think about it. You have a huge velocity back there. Remember the U squared term? There it is, right there. But you don't have any conductivity unless you do something about it. Well, you've got a little. So you see what I'm saying? It's like, could I take advantage of that detonation to actually pull energy out of there? I don't know. These are some interesting thoughts. Maybe some of you will build on them and turn it into a power device. By the way, if you want to learn about this area, I can say, and you know, with a lot of confidence, we probably have the biggest set of information on MHD for power anywhere because our lab ran the early MHD program. And since it's late in the day, we'll just tell a fun story about it. It was literally 30 years ago, right, that all that work was done. And the program closed because it just looked like, I don't think we can get there relative to the other technology options we had, IGCC. So all that data was boxed and stored and went in our best record-keeping systems 25 and 30 years ago and sat there. And then we started thinking about this about 2 years ago as a technology, say, well, maybe we should look at that. Well, let's go find all those records. Did you ever go into a government facility and ask for records from 25 years ago? They're there somewhere. They were, right? But we had to do a little looking, right? Because somebody moved something and, well, lo and behold, my buddy Rigel Woodside finally found them and looked at the tag that said, to be destroyed 3 weeks later. Is that amazing or what? This is a true story. I don't know if it was 3 weeks or 3 months. I've got to be clear here. I can't remember, but I mean, it was frightening because we thought, well, if we hadn't went and looked and found them, they would have went to like nobody's interested in this anymore. So we've actually gone through the process of going through all those 94 boxes. It was a great thing for one of our summer students, and yeah, we've digitized them. So anyways, if you unfortunately, we cannot make them publicly available. Believe it or not, there were some copyright issues on some of them, so we couldn't get permission to do that. But if you discover that you're starting to work in this area, we have all that information, and you just need to get in touch with one of us at the lab, and we've been going through those. So interesting little side story there, huh? All right. So we're going to wrap up here about 5 minutes early, but you know, if you've I've piqued your interest and you want to see, well, did I really catch, you know, what was being said today? Just a couple of simple things you can go home and do and try and figure this out. Like, try and convince yourself how this disk generator works, because it's just very simple. You can do it on a piece of paper. Take U cross B. Figure out that's the voltage that I'm generating from the magnetic field interacting with the velocity. Figure out where the Hall current goes, and then figure out where the voltage goes. And I already gave that example, and you could just draw a picture of that. And then think about what happens if the flow is swirled going in there. And you just have a lot of fun thinking about that and see if you can do it. Just draw a sketch and convince yourself you know what's going on. But I'll mention there are people that would say you could take advantage of that swirl, or who would realize the flow is going to get swirled by its interaction with the electric and the magnetic fields. Right? It's not going to come out straight because it's got a force on it, so it's going to start it swirling. So you actually have a chance to take advantage of that if you configure the flow field correctly relative to what's going on with the magnetic and electric field. And this is just a fun one. Go out to the internet. You know, the guy who dreamed up the idea of doing MHD was Michael Faraday, and you know, he realized, wow, you know, if you just have a river flowing, it's got some conductivity, and it's sitting on planet Earth, and you have a very modest magnetic field, and if you stick 2 wires in there, you ought to be able to measure something. And he did, but he didn't measure what he thought he was measuring. So you can go in and read the account of that, because what he was measuring was probably more just, you know, the electrical potential from other things that were there in the river. But it's still an interesting account to read and understand. Yeah, you could think about that. Well, I finish up here, you know, other situations in nature where MHD physics is doing all over the place, right? I mean, for people who do astrophysics, they have to worry about this, right? Because there's magnetic fields around stars and there's conductive plasmas, and it's a huge issue. And what I've told you today about MHD is just one limiting case. Because what I didn't mention all the way working through it, we're looking at one limiting case of MHD here where the magnetic field is not corrected because of the current that flows. It's too small an effect to count for an MHD. That's not true like in stellar applications and other places. Once you start the thing moving, then you have to count for the current. The magnetic field is generated by that flow of current as well. So it feeds back on itself. And that's why people who try to do plasma have really a very challenging assignment to figure out the hydrodynamics of the flow in those environments, because they're not as simple as the one I've described today. As if that was simple. Hard for me. All right, I think we are done, and I'll take any, oh, well, there's just a summary there. I'm trying to popularize the word direct power extraction just to say we're doing something different than what people did when they say MHD power, because I don't want to do what they did 20 and 30 years ago. I say, is there something fundamentally different we can take advantage of due to advances that have happened today and the fact we have different drivers for CO2 capture? So, you know, I've already been through this, you know, idea of conductivity. Well, maybe there's some chances for a new innovation here. The other things that have changed, I've mentioned again and again, computational models. And what we're trying to do is just get started using simulations and a few validating experiments with maybe new materials, new processes to make those materials. Can we make this work? Is it a useful power generator for tomorrow, all right, where we could manage CO2 at very high efficiencies? So we'll see. I hope some of you will somehow get involved. Maybe we'll be able to have a larger activity in this area. It's small right now, But it really is a new development in combustion technology that, well, I hope I've explained enough to get you an introduction, and we'll see where it goes from here. Any questions in the last few minutes? You're probably wanting to go, but a question maybe for the whole audience. Pause and look around for a minute. Anybody? No? Go ahead.
So, I mean, the efficiency for direct power extraction, you said scales is U squared, V squared, but also drag, I mean, you're extracting whatever energy, if they're high velocities, they're drag.
Yeah.
What are some comparative numbers?
Oh, what's the pressure loss? I don't have a way to give you a good number. I just don't know that number. I haven't done that calculation. I would say even before drag, though, there's heat loss. That's even worse. That I know is going to be significant percentages of the total output, because why? You've got to keep the electrodes cool enough. All right. Now, granted, the time scale of transit down there is not real great, but you're going to get thermal loss, and I think that's even more of an issue than, just fanning friction losses going down that too. But great question. Great question. Anybody else? If not, you probably want to get to dinner. But this has been fun. I appreciate your patience on maybe some long talks here, but lots and lots of fun. So thank you, guys. Thank you.
Thank you for your talk. I did have a question. I didn't really want to ask it.
Oh, yeah.
Anyone else.